All right, so this is the video lecture recording for Algebra 2, Unit 3.8, all on imaginary numbers. So again, reminder, we did introduce imaginary numbers a little bit earlier here, but now we're going to have an entire section devoted towards it. All right, and again, there are 3 quizzes at the end, but I like it because it's a little bit more focused on what each of the quizzes is on. So first quiz is on imaginary numbers in general. Next one is on operations on complex numbers. And then the third one is on quadratics with complex solutions. So let's get started. All right, with the overview here. Basically, what this is saying is that we've stepped up, and if you want to go through a natural progression of more complex mathematics, right, started with counting on your fingers, then we started doing negative numbers, square roots, irrational numbers, and then really we came to problems we couldn't solve. So we had to come up with these things called imaginary numbers. And when we used these imaginary numbers, we were able to solve more complex or different mathematical problems. So we're going to really dive into what imaginary numbers are, and figure out how we can use them. All right. And this tells you it, and I'll just preview it for you. Imaginary numbers do have real applications, even though they are considered imaginary, right? They help us explain the world around us. So it's saying that, hey, these are imaginary. You have to pretend like they're there. But if you were able to do that, then this, and this, right? So we'll work on understanding more about that throughout this lesson here. All right. Now, imaginary numbers, okay? Imaginary numbers are important because they are used frequently in polynomials. They're used to explain, like I said, things that aren't exactly there, but they are needed mathematically to make the problem work. Now, before we can get started, we got to review square roots. So we talked about this earlier, so I'm going to flash through this real quickly here. Square root of 16 is plus or minus 4 because if we took the square, if we squared 4 and negative 4, they would both give us 16. Same thing here, 49 is plus or minus 7, right? Because if I squared negative 7, it's still going to give me 49, all right? Same thing if with the positive version of that, all right? But what happens is if we try to take the square root of a negative number, we have an issue because if I took 2 squared, it's still going to give me 4, or negative 2 squared, it's still going to give me 4. So there's no real solution that if I took the square root is going to give me a negative, if I took the square root of a negative value is going to give me a real number, right? Or there's no value that I can square to get a negative value, all right? So this is where we have to get a little bit creative here, and this is where imaginary numbers come into place. All right. So what happens is if we have x squared plus 1, right, we can have negative 1 on the other side, and we can take the square root of both sides, and we end up with x equals the square root of negative 1. All right. Now, where there's no real number that we can get this here. So what we did is we invented this thing called imaginary numbers, right? So we invented imaginary numbers, and so the square root of negative 1 is what gives us this imaginary number. So we said that the square root of negative 1 is going to represent this imaginary number, which we call I. All right? And what we can say then is if I is equal to the square root of negative 1, then I squared is equal to negative 1. All right? Then I squared is equal to negative 1. All right? And then we move forward with that there. All right? So again, showing you, we can move 1 to the other side. We can take square root of the negative number, and what we say is hey, square root of negative 1, we're going to call that this imaginary number I. All right, and we treat it just like a variable, which is why I love it. We treat it just like a variable, so it's not anything that you should be, completely freaked out by. All right, we treat it just like a variable. So when we are looking to find the square root of negative numbers, we have some defined steps here that I'm going to walk you through. All right, we factor out the square root of negative 1. All right, that's step 1. We can factor out the square root of negative 1. Right, we can substitute in I for the square root of negative 1, and then we can take the square root of the positive number. Right, and then when we're done, we write the final product there without a multiplication sign. So what that looks like here, first step, we factor out a square root of negative 1. So looking at this, if I had the square of 4 multiplied by the square of -1, that would give me my square root of -4, right? That's one of the rules of multiplication there. All right. So what then we then say is, hey, we're going to substitute an I for negative square root of 1. All right, so that turns into I. Then we now can take the square root of 4. We know that that is 2. All right, and then we get rid of this multiplication sign. So what we can say is the square root of -4 is equal to 2I. All right, if we're going to do this one for -9, all right, the first step there would be to factor out the negative square root of 1. So we're left with the square root of 9, and we know, or we can figure out easily if you need to, right? We can hit Control square root button. Our square root of 9 is equal to 3. So we are having 3I. And again, because I is equal to the square root of -1. Square root of -1. So that should be your answer. All right. So then, again, here's a couple more examples of how to find negative square root. So -64, factor out the -1, change that -1 to I, and then you find out that the square root of 64 is 8. So you multiply together, that's 8I. -9, you factor out the -1, change it to I, square root of 9 is 3, you have 3I. Okay, 121, factor out the negative square root of 1, change that to I, you got 11I. Okay, so moving forward here, we can find out that, hey, we can take I and treat it like a variable, but if we multiply a certain number of i's together, we're going to get back out numbers, right? So what I mean by that is we said that, hey, if I have I, that stands for the square root of -1. Well, if I have I squared, that's effectively canceling out my square root there. So I squared is equal to -1. All right? And if I want to look at what happens to I cubed, right, what I can do is I can pull out, this is like saying I squared times by I to the first, right? Well, I squared is equal to -1. So then -1 times by I gives you -I, right? And even taking it one step further there. Okay, if I want to do I to the 4th, this is like saying I squared times by I squared. So -1 times by -1. Well, that gives me 1, right? 2 to the 5th, all right? That's like saying I squared times I to the 4th times I. Well, we just found out I to the 4th is 1. I by itself is I, right? So this is saying I. And what you're going to notice here, or what you're going to find out here, is that there's a pattern. All right, there is a pattern. Okay, it goes I -1, -I1, I -1, -1 I, -I1, right? It just repeats these 4 right here. I -1, -I1, I -1, -I1, right? It'll repeat itself over and over again as we continue this power up. All right, so this is what it'll look like, okay? And what we can do then is if we have something really large, like 37, we can break this up into smaller and smaller factors because I to the 4th is equal to 1, right? So effectively, if I break this up, right, 4 times by 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 36, right? So I have 36, and I need 1 more. So I have to multiply by I to the 1st. So that gives me my I-37s. Well, effectively, all of those turn into 1s. So I'm just left with I by itself, right? And as we know, I by itself is going to give me I. So I to the 37th really just boils down to I, right? And again, this table is going to be incredibly helpful for you. So it's going to be, I believe, on your study sheet. It's going to be on a lot of different places. So make sure that you have this handy and know how to use it. All right. Now, imaginary numbers explain what happens when you take the square root of a negative number. All right, a negative number. Now, imaginary numbers, again, are the square root of -1, and it's represented by an lowercase I. Again, it's specific, lowercase I, cannot be capital. Okay, and the pattern there that we just talked about, it goes from I, -1, -I1, I, -1, -I1. It repeats over and over again. Because what we can do is we can break it up into little tiny patterns of I to the 4th, because all of those will cancel, and whatever we are left with, that will give us what our value is. All right, square roots of negative numbers. All right, so square roots of negative numbers. All right, so for example here, right, this is a perfect example. We would break this up, so we factor out the negative square root of 1. So this would be square root of 144. So if you have your calculator and you need to know what it is, square root of 144, that's 12, right? So I'm going to have 12, and then I factored out a a square root of -1, and square root of -1 is I. So your final answer for this would be B. All right. And then this guy here, the powers of I, the powers of I. So let's go with I to the 22nd. All right, so again, you're going to try to break this up into as many I to the 4ths as you can, because if you can remember that pattern, every I to the 4th actually just stood for 1. So my way of doing this is I go 22 divided by 4. All right, well, I have 11 and some chains. Or, sorry, I have 11 halves. All right, so 11 divided by 2. This gives me 5.5, right? So it's saying I can have 5 of these with a couple left over. So 4 times by 5 is going to give us 20, right? So I need 22. So that means I have all I to the 4ths, but then I end up with an I squared, right? And so if I have I squared left over, according to my pattern, I squared is going to give me -1. All right, so that ends up actually being -1. All right. Right here, I to the 16th. Well, we know that 16 goes into 4 evenly 4 times. Ooh. 16 divided by 4 goes in evenly 4 times, right? And if we're looking at our pattern, I to the 4th is 1. So this guy, I to the 16th, is equal to 1. All right, and you can do the rest or the last two there. Okay. So moving forward here, again, it's about factoring. Okay, factor out, follow those steps. Make sure that you understand what I stands for. Okay, so for this one, again, you'd factor out the -1. You'd go square root of 169, which is 13. So your answer here should be C. It should be 13I. All right. Equivalent of the expression below, right? This is, again, we're trying to figure out how many times does I to the 4th go in. All right, and for this one, it would go in 2 times, right? We would go in 2 times. So again, 4 times by 2 is 8. So I go 11 minus 8 gives me 3. So what that's saying is I'm left over with I to the 3rd, right? And according to the pattern, I to the 3rd is actually equal to -I. So that should be C there, right? And it gives you an explanation. Very good, because it's equal to the 4th to the 4th to the 3rd. 1, 1, -I. All right. Now, with real numbers, it says it's a cousin. It's a cousin, right? Because it's very same. It's very similar, very the same, except for it's multiplied by this imaginary thing called I, right? So moving forward here, we have these things called complex numbers, right? It's imaginary numbers are part of this thing called complex numbers. All right. And complex numbers are made up of both real and imaginary numbers. All right, real and imaginary numbers or parts. All right, and they're written as we talked about earlier in the form a plus or minus bi, where a is a real number and bi is an imaginary number. All right, b can be a real number, but I is what makes it the imaginary part. right? So this is what we call an imaginary number. Now, each of the numbers below is a complex number, and do you know why, right? So the first ones are kind of obvious, right? Well, it's in that form a plus bi, a plus or minus bi, right? It's kind of obvious there. But when we get to these back halves, it's kind of more difficult. So look, if you look at the examples, 0 plus 0i, well, technically that's still 0, but that turns it into this a plus or minus bi form, right? Same thing with 15. Technically, it's 15 plus 0i, which makes it a complex number. And then finally here, 2i. It's just like saying 0 plus 2i, right? So truly, every number you've ever seen in your life is actually a complex number. It's just whether or not you can see the other part. Is it a 0? Is it there? Is it not? All right. So then moving forward, right, just like real numbers, I told you that we're going to treat imaginary numbers like we're going to treat them like variables, right? So we can actually add, subtract, multiply, divide, and we're going to walk through real quickly how to do that. So if we're adding here, when we're adding complex numbers, you just combine the like terms, right? You simplify, and then you call it a day, right? That's how we add the complex numbers. You're going to do the same thing for subtracting. You're still going to distribute the minus sign, you're going to combine the like terms, and then you're going to simplify, right? You're going to distribute, combine, simplify. All right. So here's a more broken out version if you want to see that on your own. Okay. So for this one, straightforward, rearrange, simplify. For this one, distribute, rearrange, simplify. All right. And we can think of complex numbers as binomials, right? So by that, it means you can use the FOIL method to really expound that or even simplify depending on which direction you're going, right? So for example here, if we're going to multiply these two complex numbers together, right? We're multiplying these two complex numbers together. We're going to multiply the first. So 4 times by 6 gives us 8. 4 times by 2 gives us 8. We do the outer. So 4 times by negative 2i, right? So we just focus on 4 times by 2 gives us 8, and we still have I there. All right, then we do the inner. 6i times 2 gives us 12. And then the last one there, 6i times by 2i. So that gives us 12i squared. All right, and 12i squared. So then we're just going to combine the like terms for the next step here. All right, so when we combine the like terms, we get 4i. Now, I squared equals something special, right? And we got to remember our pattern. I squared equals something special. It equals -1, right? It equals -1. So because it equals -1, we can substitute that in where we have 12i. Okay, so we replace it, and then we simplify. And if we can, again, we can combine like terms or simplify further. All right, so again, what this might look like here. FOILing out first, outer, inner, last, combining like terms, replacing I squared with that -1, simplifying again, and then we get our final answer. Okay, now that we understand a little bit more about these complex numbers, there's this thing called complex conjugates. All right, complex conjugates. All right, and what a conjugate means is that it's the same but different in one aspect. And the way that it's going to be different with these complex conjugates, it uses the same variables, the same numbers. The difference is that in one you're going to add them, and the other one you're going to subtract them. So 3 minus 2i, its complex conjugate is 3 plus 2i. And what happens is when we follow the same process and we FOIL out our two complex conjugates, what actually happens is that middle value, which would usually be, our bi, that actually gets canceled out. And then when we replace our I squared with the -1, we are able to actually get a solid 1 value out. So what happens with complex conjugates is we're able to cancel out and we're able to get a value. Right? So if we look at how this is done here, okay, again, we're looking at complex conjugates. Okay, so I'll let this go through and then I'll talk you through it here. Okay, so what's able to happen is if we look at this fraction here, okay, it looks pretty daunting to try to simplify that, right? But what we can do is we can multiply the entire equation, the top and the bottom, by the complex conjugate of our bottom, right? And what happens is if we're just looking at the bottom for a second, right, we end up being able to simplify, right? 2i minus 2i, that cancels out. I replace my I squared with my -1, that turns that to 4. I'm able to simplify the bottom into just 5. All right, and when I look at the top here, I FOIL this one out, I combine like terms, I replace for I squared, and now I've got -4 plus 7i. And that one is a lot more manageable than the top number here. We're only dealing with one complex number. All right. And then the final step here, what they showed you here is that if you have a quantity on top and one solid number on the bottom, what you can do is you can divide both of those by the denominator in order to show potentially an easier fraction if this was something that could be reduced. So hopefully we'll get to a problem here where that makes sense. But -4 divided by 5 plus 7 divided by 5i. All right. So looking at what this looks like again, so you start with the normal, right? You start with the normal. Okay, you multiply by the complex conjugate of the bottom. So all you do is you change the negative, right? You got to multiply the top and you got to multiply the bottom because you've got to make sure that you are consistent. All right. When we look at the bottom here, the complex conjugate ends up canceling out, right? So the 7 i's cancel out. 49i squared. We replace the I squared with a -1, right? And this simplifies down to just the number 50. When we look at the top here, we FOIL out, okay? We FOIL out those two quantities. We combine like terms. Okay, we replace the I squared with a -1, and then we are left with 17 minus 19i on top. All right, and then what we're able to do is divide both of those top numbers by 50, and we get our final answer. 17/50 minus 19/50 I. All right. So complex numbers are made up of real and imaginary parts. Okay, a complex number has a plus or minus bi, where bi is an imaginary number. All right, and then how do we subtract, multiply, and divide? Right, we treat I as a variable and we combine like terms. When we're multiplying, we FOIL, we combine, we replace I squared, and then we simplify. And when we divide, we multiply the top and the bottom by the conjugate of the denominator, and then we simplify. All right. So again, being able to do the operations on complex numbers, that's going to be an entire quiz in this section here. It's going to be a quiz in this section. So again, for this one, it's just simple addition, okay? So you're going to add them straight. You're going to combine like terms and simplify from there. All right? For this one, remember, we've got to distribute the negative sign. Then we combine like terms, and then we simplify. All right, for this one here, we got to FOIL, right? We're going to FOIL, and then remember, we're going to get an I squared, which we can then replace with -1. All right, and then finally for number 4 here, dividing by the complex numbers, right? You've got to multiply by the complex conjugate, which is 2 plus I, right? And then you should end up getting a solid number on the bottom, right? You're going to get a solid number on the bottom, and then you will end up with a simpler version on top. Okay, and then once you get that bottom number, you divide the top, both those numbers, by your denominator, and you will end up with something that looks in the form of this. Okay, and obviously you've got to make sure you do the math to make sure you get the right values here. Okay, so then our last little section here, which is going to be that final quiz in this unit, solving a quadratic equation by completing the square. All right, so we worked a lot, we worked a lot on how to solve quadratic equations. We worked a lot on how to solve quadratic equations, right? And we've done it through a various number of methods, right? And this first one we're going to talk about here is completing the squares, all right? But now we need to talk about what happens if, when we complete the square, we end up with an answer that has to involve an imaginary number. All right, so when we are trying to complete the square here, all right, we can try to complete the square. We can subtract 14 from both sides, right? When we complete the square, though, we're then looking to divide this by 2 and square that, right? So we're going to end up adding 1 to each side so that we can get our square here. Then we're going to take our square root of the entire equation, all right? Which simplifies the left-hand side, makes that easy, but it doesn't simplify the right-hand side necessarily, all right? But you can see they already replaced it. So negative square root of negative 6 turns into square root of 6i, right? We change that to square root of 6i. Then again, we have the positive version and the negative version, and then we end up solving by adding 1 to both. So our two solutions are 1 plus square root of 6i and 1 minus square root of 6i. And again, if 6 was something like 16, where we could reduce it further, then you would do that. All right, moving forward here, we're going to look at another quadratic equation, but this one can't be solved without using imaginary numbers, right? And you have to use the quadratic formula to find this solution, right? You cannot complete the square for this one. All right, so if we start off with our equation here, we're going to add 17 to both sides, because in order to use our quadratic formula, you have to be in the standard form. All right, so now we get to our standard quadratic form. We are able to plug in our values to the quadratic formula based on our a, b, and c values. All right, we are able to then simplify. Okay, and we can simplify further, and we result in square root of negative 16. So immediately we know we're going to have two imaginary solutions here. All right, when we simplify further, all right, when we simplify further, though, remember, this is a perfect example of we've got negative 16. So if I take out that negative, square root of 16 is 4. So this is like saying plus or minus 4i. All right, then what we can do is we can simplify even further, right? So this is a perfect example of I would take negative 6 and divide by 2, and that actually simplifies. So I have negative 3. And I can take 4 divided by 2. That gives me 2i, right? So my two answers here would be negative 3 plus 2i and negative 3 minus 2i. All right. So looking at this quadratic function here, there are multiple ways for you to solve some of these quadratic functions, and truly it's whatever you're most comfortable with, right? So for this one, you could add 4 to both sides, take the square root, find out it's plus or minus 2i, right? Or you could do the long quadratic formula to figure out that it is plus or minus 2i. Or you could rewrite it, if you remember all the way back many, many lessons ago, to difference of squares, right? So the a squared minus b squared, right? A squared minus b squared. And you're saying that b squared in this case, you're saying b squared is negative 4, right? And so b by itself would have to be 2i, right? And if this one confuses you, by all means, you do not have to do this one. But if you really liked this, by all means, go ahead, right? But again, you have multiple ways of figuring out the answer to the same quadratic. All right, so then looking at more complex answers here. Okay, complex answers. This is again where we have the conjugates. Okay, we have the conjugates. And I'm not going to spend a whole ton of time here. This is just trying to show you that with the quadratic formula, if we were to use FOIL with our complex conjugates, okay, if we were to use FOIL with our complex conjugates, we would end up finding out it looks very, very similar to our original term here. All right, it looks very similar to our ax squared plus bx plus c. All right, now, one of the things I do want to point out to you, though, is for quadratic equations, okay, for quadratic equations, if you are going to have an imaginary number, you have to have 2 of them. You have to have the complex conjugates, right? You can't have one imaginary number without the other. So for example, a is got 2i, and its complex conjugate is minus 2i. So this one is a possible root. Same thing, 8 plus I, 8 minus I. Those are complex conjugates. But 3i and 5, those are not conjugates of each other. So they would not be answers to a quadratic equation. All right. 7 plus I and 11 minus square root of 7. Those are not complex conjugates. However, 17 plus 2i and 17 minus 2i, those are complex conjugates. All right. So you got to make sure you're very, very specific here with what you're looking at. All right. So again, that ends the review session here. Okay, now we're going to look at the study guide and the concept check. All right, quickly here for the study sheet, imaginary numbers. So an imaginary number is the square root of a negative number. All right, and the letter I stands for the imaginary number square root of -1. Square root of -1. All right, and that's kind of our go-to here is I, because it's going to let us be able to cancel some things out because we found out there is a pattern, right? So what we can do to figure out the square root of a negative number. So we factor out a -1 to make it a positive. Then we can substitute I for that square root of -1. Then we can take the square root of the positive number and then write the product without the multiplication form. So again, factor out -1, change that -1 to an I, factor out or factor the square root here. So we get 2 times by I and then write it without that multiplication symbol. All right. Then what we found out here is there's a pattern. There's a pattern. So I stands for I, right? We said that. Okay. I is representative of the square root of -1. But if I have I squared, right, it's like saying the square root of I squared squared. So that cancels out. So I have -1. I cubed is I to the 4th is 1. And then, like we said, this repeats the pattern for the 5th one here. So it starts back up with I. And the reason that is because we can break these down into smaller units. So like I cubed is like saying I squared, which is -1, multiplied by I. So that gives me -I. I to the 4th is like saying I squared times by I squared. So -1 times -1. That gives me +1. All right. And then when we go back to the 5th, we have the 4th times by I, right? So 1 times by I gives me I. And then, like we talked about, what we can do is break this down into smaller units. So we know 13 breaks up into I to the 4th 3 times, and you have 1 left over. So you have 1 I left over. So this breaks down to 1 times 1 times 1 times I. So I to the 13th is I. All right. Now, for real or imaginary, okay, a complex number is a number that can be written in the form A plus BI, where A is a real number and BI is the imaginary number. So real, imaginary, okay, and it's plus or minus. Okay, so if we write this complex number, okay, so in the A plus BI form, that one's pretty obvious here. The real part is 1 and the imaginary part is 3i. Now, if we have 2i, if we're writing it in this form, it's technically 0 plus 2i. 0 is the real part and the imaginary part is 2i. For 15, that is the real part, okay, but we would write it as 15 plus 0i, so 0i would be the imaginary part. Now, rules for operations with imaginary numbers, okay? For addition, you treat I like a variable. You just combine like terms. For subtraction here, you have to distribute the negative sign first throughout, then you combine like terms. All right? For multiplication, you're going to treat the complex numbers as binomials, right? So as binomials. So you would FOIL this guy out. FOIL to multiply, substitute in. For the I squared, when you get to that point, you substitute in -1 for I squared, and then you simplify. All right, and then finally for division, you're still treating it like a binomial, but we're going to multiply the top and the bottom by the complex conjugate of the bottom, right? So 1 plus 7i, its complex conjugate is 1 minus 7i, right? And what that allows us to do is if we focus on the bottom, it allows us to cancel out those middle terms, change I squared to -1, and then get a single number on the bottom, all right? And when we look at the top here, we are able to FOIL this top part, combine like terms, and simplify, right? And then the final step there is we have to make sure we write this as a complex number. So again, focusing on, you've got to have a real part and imaginary part. So you divide both of the numbers on top by the denominator on bottom. All right. And we're going to go then into the checkup. So again, reminder, you've got 3 quizzes on imaginary numbers, operations on complex numbers, and the quadratics. So actually solving those quadratics. All right. So we'll move to the checkup here and get this then started for 3.8. So we'll look at the checkup now and we'll work through some problems. All right, so we're going to work through a couple problems here, and I'm going to highlight some things that weren't really discussed or were kind of glossed over here within the lesson. So for the first 2, we'll go through both of these and show you what this looks like. So, right, one of the first steps it said was to factor out that square root of -1, right? And then we change that to multiplying by I. Right, and then we can factor that first one. So square root of 121 is 11. And then when we write it, we get rid of the multiplication symbol. So that turns into 11i. All right. Now, this next one here is something that maybe we've talked about, maybe you've talked about ever. If you haven't, we'll briefly talk over it here. Okay, so square root of -18. All right. So if we were to factor out that -1, the reason we can factor that out is because it's like saying 18 multiplied by -1. All right. And what we can do here is if there's 2 things that multiply together and one of them's a perfect square, we can even simplify this further. So what I mean by that is to get 18, we multiply 9 by 2, right? And that would give us 18. And so we can keep that -1. So what this is saying is square root of 9 multiplied by square root of 2 multiplied by square root of -1. All right? And that's what that's looking like. So if we simplify all of these at the same time, the square root of 9 is 3. We can't simplify the square root of 2, so that stays as it is. But, the square root of -1 turns into I. So what this actually looks like is 3 square root of 2i, or 3i square root of 2. Both are acceptable answers. All right. And the reason that I'm showing you that is because I don't want you to get tripped up if you see that online or if you see that as a potential answer on your computer scored tests. Okay. So both of those are acceptable answers. All right. And then, of course, obviously, if neither of those are answers that are allowed, okay, you could say square root of 18i. That is also acceptable. But if it can be simplified further, okay, you should do it, right? So we knew that 18 was 9 and 2 mixed together, and 9 was a perfect square, so we were able to simplify that further. All right, so for this one here, I'm going to do the first one, and then you guys can do the large one if you'd like. All right, but basically, I to the 17th power is like saying I times 4 times I times 4 times I times 4. That gives me 16, right? All of those is 16. It's I to the 16th, so I need one more multiplied by I. So again, what this is saying is 1 times 1 times 1 times 1 times 1 times I. So I to the 17th is simplified as just my lowercase I. Right? And again, that is based on my repeating pattern for the powers of I. Right? And that's going to be really helpful for you guys. Okay? Moving forward here, perform the following operations. All right, so I will do what I think are the more difficult ones. I'll do 6 and 8 here. All right, so for this one, for subtraction, I have to distribute that negative sign first. So 5 minus 2i minus 3 minus 4i. All right. Now I'm going to combine like terms. So 5 minus 3 minus 2i minus 4i. Right? 5 minus 3 gives me 2. And negative 2i minus 4i gives me negative 6i. All right. Now for 8 here, okay, 7 and 8 are identical. So you're going to FOIL, or I'm going to FOIL. So 3 times 2 gives me 6. 3 times 3i gives me 9i. Negative I times 2 gives me minus 2i. And then finally, negative I times by 3i gives me minus 3i squared. Okay, gives me 3i squared. So now, when I combine my like terms, 6 plus 7i minus 3i squared. All right, I'm going to then replace my I squared with my negative 1. 3 times by negative 1. So 6 plus 7i plus 3. So I am left with 7i plus 9. Or the way that you should write it to be in the correct form is 9 plus 7i. Okay, remember, we got to make sure it's in that A plus or minus BI form. All right. Okay, question 9 and 10 is based on division here. So I will do one of these and leave the other one for you. All right. So, okay, what we do is we multiply by the complex conjugate of the denominator. So 4 minus 5i over 4 minus 5i. All right. And what we can do is we can take this step at a time. So I'll focus solely on the bottom equation first. All right. But let me combine this. It looks like 5i, 4 plus 5i, 4 minus 5i. All right, so moving forward, okay, if I move forward with the bottom, I'm going to FOIL. So 4 times 4 gives me 16. All right, minus 20i plus 20i minus 25i squared. All right, minus 25i squared. Again, just focusing on my denominator, and I'll put a little arrow so we know the different steps. Okay, those middle numbers cancel out, so I've got 16 minus 25i squared. All right, I replace my I squared with a negative 1. All right, and if I keep going here, I'll turn sideways. There we go. All right, I've got 16 plus 25. So my denominator turns into 41. All right. Now if we go through the top, right, we're going to FOIL the top. So 2 times 5i, that gives me negative 10i. Okay. Oh, and I messed that one up. Sorry, I should have done the first one first. So 2 times 4 gives me 8 minus 10i plus 12i minus 15i squared. All right, I'm going to combine my like terms. 8 plus 2i minus 15i squared. Okay, then I'm going to replace my I squared with a negative 1 plus 2i minus 15 times negative 1. 8 plus 2i plus 15. So I've got 23 plus 2i over 41. All right, over 41. Now, again, we've got to simplify this. All right, so the final step is I've got to write it as 23 over 41 plus 2i over 41. All right, so that is the simple